actually not a climate change scientist. I'm not an atmospheric scientist. But I am a mercury and carbon biogeochemist. And what that basically means is that I study the way mercury and carbon atoms move in our environment and how they move from different compartments to like the atmosphere, to water, and within those compartments. And of course, those ecosystems are very much impacted by climate and climate change. I am, however, a science educator. And so increasing science literacy has been a passion of mine for quite some time. And as such, my goal today is to kind of present 3 lines of evidence that will show you that the role of humans in the changing climate is real, it is strong, and it really can no longer be denied. So I'm going to talk about 3 main things. The first is I'm going to talk about concentrations of greenhouse gases. You hear a lot about greenhouse gases, I'm sure. And I'm going to talk about their role in our climate. And then I'm going to talk about the chemical nature of carbon dioxide, which has changed since the Industrial Revolution. And then I'm going to give you a whole bunch of examples why we truly know that things are changing. And I suspect I'm maybe talking to a lot of people that are already converted to this idea, but I'm going to end off the talk talking a little bit about some of the things that maybe we can do to help with this climate crisis. It starts with the sun. I'm going to give a little bit of an introduction on how our atmosphere makes the life that we know on Earth possible. And so isn't this a fantastic picture of the sun? It's actually 2 pictures. But the intent of the photographer was to have a very detailed picture of the sun and have the International Space Station silhouetted on top of it. So way at the top there you can see the solar panels of the International Space Station. And it's a really fantastic picture that I just couldn't help but show. So in order to get started, I'm going to start off kind of with Atmosphere 101. So the sun provides all of the energy that we need and use on Earth. And once that sun's energy reaches the Earth, it is absorbed by the surface of the Earth, and it is changed from short-wave, high-energy radiation into long-wave radiation, which we experience as heat. This heat is radiated off the surface of the Earth, which means that the Earth warms from the surface, and once it hits the layer of gases in the atmosphere, that energy is transformed and re-radiated in all directions, including back out into space, but more importantly, back down to Earth. And so that is what we talk about when we describe the greenhouse effect. We have a really good example of how the greenhouse effect allows our planet on Earth to be so well, maybe not today, but habitable in the moon. And so this is another really fantastic picture. This is, in fact, a composite of 500 images that this gentleman put together of the moon, and you can see the reflection of the light onto the moon. The moon is pretty much the same distance away from the sun as the Earth is. And so, as such, it gets about the same amount of energy. And yet, we know that there is really no reason to live on the moon. Aside from the fact that there's no oxygen to breathe, it's really cold and dry. So we have this example right next door that shows us that our atmosphere is really important in making our climate so habitable. So these are kind of the main gases that we find in the atmosphere. So they include water, as well as nitrogen gas, oxygen gas, argon, which is an inert gas, and ozone. And these all play roles in our biogeochemistry of the Earth. Biogeochemistry is basically the way that matter moves in our environment. But they don't really have a lot of role in the greenhouse effects. Instead, we have a number of gases that are present in our atmosphere at much smaller quantities, including carbon dioxide, which you hear a lot about, methane, nitrous oxide, and chlorofluorocarbons of many different types. And these are all collectively referred to as radiatively active gases. These are the gases, the molecules that transport or allow that long wave heat radiation to be redirected back onto the Earth's surface. And they do so at different potencies. So there are rags, as they are called sometimes, on the side there, and they have a different ability to re-radiate this heat, and so they have different potencies. Carbon dioxide is kind of the benchmark. It's set at 1. And then we have methane. Methane is a 21 times greater greenhouse gas than carbon dioxide. Nitrous oxide, N2O, which is released from soils and dentist offices. My daughter just had a filling last week and she was really happy about the N2O. In fact, she doesn't really want to brush her teeth anymore because she liked it so much. But anyways, that gas is 210 times stronger as a greenhouse gas compared to carbon dioxide. And then we have these chlorofluorocarbons. Chlorofluorocarbons are an industrial compound. They did not exist before we started to make them as a society, and they are very potent greenhouse gases. Many of them contribute as well to the destruction of ozone in the stratosphere. So we have all of these 4 radiatively active gases, but really all we hear most of the time is about CO2, maybe a little bit about methane if you're really paying attention. There was a study out the other day talking about the source of dentistries, for dentistry offices for the nitrous oxide, but really it's all about CO2. So it is kind of the main greenhouse gas that we hear and we're most concerned about. So why do we care about CO2? Well, carbon dioxide is incredibly important in how life on Earth functions. So while the radiatively active gases are really important in making the climate such that the temperature is in the right zone for water to exist as a liquid, our biosphere uses that carbon dioxide as well as the water to provide energy for all of life on Earth. The sun is the provider of all this energy. That sun's energy is not usable for life on Earth. It needs to be transformed or fixed into a source of energy for virtually every organism on Earth. So it's very important in our life, and it has a number of, we call them sinks in biogeochemistry. And basically what a sink is it's a place that the molecule of interest, carbon dioxide, ends up after any sort of metabolic, physical process. So one of the main sinks of carbon dioxide, I've already mentioned, is photosynthesis. And photosynthesis is, of course, CO2 plus water, which makes glucose and oxygen. This is the energy that is provided to all living organisms with the exception of a few. And I'm just not going to say that anymore. I do know I'll go back to it. The other sink, the other fate of CO2 is to be dissolved in the oceans. So in this case, CO2 is dissolved in water, and it forms basically ions that eventually kind of form weak acids. And as such, these two compartments, photosynthetic life and oceans, act as a sponge to suck the CO2 out of the atmosphere. These are both processes that have been going on since photosynthetic organisms evolved and since kind of the oceans were at the same area. Those are the sinks. That's the fate of CO2. But there are also sources of CO2. And the main source is the opposite of photosynthesis. So respiration is when organisms, such as ourselves, take glucose, combine it in an oxygenated atmosphere with oxygen, or environment with oxygen, and produce CO2. We actually breathe out CO2 constantly because that is a byproduct of our metabolism, of how we get energy from that material we consume from plants and other foodstuffs. So that is a source of CO2. Another source is combustion. It's analogous to respiration in that it's basically taking any kind of organic or carbon-based molecule in an oxygenated environment and burning it to produce energy. And we do that a lot, especially on a day like today. I think today I read on CBC that we broke the natural gas record yesterday for Saskatchewan. So as would be expected, considering what we're dealing with outside. So these are the sources. So we have the sinks, we have the sources, and in a pre-anthropogenic world, the sinks and the sources are generally balanced. However, if our sources of carbon dioxide are greater than our sinks of carbon dioxide, we get the accumulation of CO2 in our atmosphere, as shown here by a very, very famous graph called the Healing curve. So this particular data set goes back to 1958. These values are carbon dioxide in parts per million on that axis. This is just a subset of the data up until, I believe, 2017, November 2019. Well, the most recent went off. And what you're seeing here is the concentration of carbon dioxide in the atmosphere on the top of a volcano in Hawaii. There are two trends here that are very apparent. And the first one is evident when you look at the red line. So the red line is basically very high resolution data that's taken at a very frequent number of times over the course of a period of time. And what you can see is there's a very distinct sawtooth pattern as we go along each year. And what that is showing is that in the northern hemisphere, where we have lots of plants, in the summer, our plants take up a lot of carbon dioxide. Basically, when those plants are sucking up the carbon dioxide, the concentrations in the atmosphere decrease, they go down. And that's what you see at the end, in the middle of the year. So when it's down, when it's lowest, that's the summer. And then in the winter, respiration happens and all that carbon dioxide, or much of that carbon dioxide, is released again. And so if you were to take a look at the data for just 1 year, you would see that the up is pretty similar to the down. The amount that's going into the plants is similar to the amount that's coming out. The other line that is probably more obvious is the fact that the average annual concentration of CO2, shown in black, has increased substantially over the course of the last number of decades. This is pretty clear data that we are seeing concentrations of carbon dioxide in our atmosphere increase over the last number of decades. Which is my first story. But that's not all there is to say about this particular story, because we're not just talking about CO2 here. So these are those radiatively active gases I showed you in the beginning, and these are the concentrations that have that they've been measured, and I'll tell you about how they measure those in a moment. But these are the concentrations prior to human industry, and modern concentrations are here. So I believe I updated that with the most recent data. We are now at 412 parts per million of CO2 in the atmosphere. We have approximately almost three times the amount of methane, a significant amount of increase in N2O, and right here, it is a very low number, 1.6 parts per trillion, but that's way more than zero. And the reason it's zero is because we hadn't invented these gases before the industrial period, and now we do. So it's not just carbon dioxide as indicated by the Keeling curve. There's lots of increases in concentrations over the last number of decades of all of the greenhouse gases that are most important in warming the Earth. How do we know this is just not a phase in the Earth's history? The Earth is pretty old. And it's gone through a lot of different types of environments and a lot of different climates over the course of the Earth's history. We have only been measuring things like temperature and greenhouse gas concentrations for maybe 200 years, and yet the Earth has been around for a long time. So how do we know that this current situation isn't just a phase and has nothing to do with the activities of people on Earth? We know because of these wonderful things called ice cores. On a glacier, the surface of a glacier is exposed to the atmosphere. And over the course of time, dust and particles will fall onto the glacial field and will stay there and will be buried with more snow and more ice. And these dust particles in this ice can be used to date air bubbles that are also trapped in the ice core back to about 800,000 years. So basically what happens is in these continental ice shields that are on Antarctica and Greenland, these ice shields have been there for multiple periods of glaciation, and as such they have a record of our Earth's history back to 800,000 years. And so that gives us an opportunity to measure the carbon dioxide in these tiny little gas bubbles that get trapped in the ice and reconstruct the temperature of the Earth using this data. So here is the ice core data from a long core. These cores are about 35 kilometers deep. They take a lot of money, time, effort to collect. And you can see in blue, this is the concentration of CO2 in parts per million on the blue axis, and a reconstruction of the temperature in Antarctica based on those CO2 numbers. We've known since about the late 1800s, because of a Swedish scientist that made the connection between the greenhouse gases and the temperature of Earth, that when concentrations of CO2 and other greenhouse gases are high, temperature is high. And so you can see in the course of this 800,000 years, we have seen a lot of variation in the amount of carbon dioxide in our atmosphere. This is where we are now. So it is very clear that this is not something that the Earth has experienced in the last 800,000 years. And we know, because of a lot of other science and a lot of other modeling and predictions, that it is because of the fact that we have been putting more CO2 into the atmosphere in the last couple of hundred years. Which brings me to my second story. The second story is about how we know definitively that the carbon dioxide increase in our atmosphere comes from plants. And to do this, I need to give you a little bit of a chemistry lesson about stable isotopes. So stable isotopes are atoms of the same element that have a little bit of a difference in mass. So I've shown carbon here, but stable isotopes occur in many different elements. And there's usually one element that is dominant within the pool. And in the atmosphere, the dominant and in other parts of the world, the dominant isotope is carbon-12. And carbon-12 is named carbon-12 because it has 6 protons and 6 neutrons with an atomic weight of 12. Now, we also see carbon-13. Carbon-13 is named such because it has 1 extra neutron. So you can see here, when you look in the nucleus, we've got an extra red dot. That red dot makes carbon-13 just a little bit heavier than carbon-12. Nothing else changes. Carbon-12 still acts like carbon-13. It's still carbon and still undergoes the same chemical reactions. It just undergoes those reactions at different rates because it takes more energy to react carbon-13 than it does carbon-12. And so in metabolic processes or physical processes, light isotopes, or carbon-12, react faster than heavy isotopes. And there's a lot of different, this is only one small part of the picture, because when we're talking about carbon dioxide, we also have oxygen isotopes. And carbon and oxygen can be a combination of different isotopic signatures, but for the intent of today, I'm just going to talk about carbon. So, for example, here is a small atmosphere with 6 carbon molecules, and the proportions are not correct because if we had only 6 molecules, there wouldn't be a heavy one. But you can see the heavy carbon, which is carbon-13, I've colored red. And in this circumstance, there is more carbon-13 or carbon-12 than there is carbon-13. So just in the pool, there's more carbon-12. Plants and other photosynthetic organisms preferentially use the lighter isotope because it costs them less energy to do so. So a plant goes through its photosynthetic metabolism, it takes up CO2, and it preferentially takes up carbon dioxide. And so carbon-12. In the plant tissue, we end up with glucose that has actually got carbon-12, and there's proportionately more carbon-12 in the plant than there is in the atmosphere. So we get an increase, it's called fractionation, an increase in the lighter isotope in the plant tissues. So this is basically showing that fractionation. In the atmosphere, pre-industrial times, the signature of the carbon dioxide was about -6 per mil. It's like percent, except it's 1,000 times less. And when you fractionate it into certain trees, and different types of plants have different fractionation rates, but the vast majority, you'll get a fractionation or a decrease in the heavy isotope such that you get to about -27. So you have these plants that have already kind of preferentially chosen these lighter molecules. And of course they die. And eventually they end up in the lithosphere under high temperature, high pressure, and low oxygen. They end up forming all of these hydrocarbons, which we know and love. And if we then pump those hydrocarbons out, the combustion of these hydrocarbons does not change the isotopic signature of the carbon. And so what happens is that we end up releasing a lot of carbon isotopes that are at that -27 per mil signature. The atmosphere is a very active place. We get mixing, and so we find that our isotopic signature of our atmosphere has changed from -6 per mil before industrial times to -8 per mil. And if you want to see the data, here it is. This is data going back to the year 1000, and it's showing carbon dioxide concentrations in red, again in parts per million, and it's showing delta C, or the amount of heavy isotope in the atmosphere in per mil. And as you can see, that about the time we started to see increases of carbon dioxide in our atmosphere, the isotopic signature started to become lighter. This is definitive data that show that the type of carbon in our atmosphere is becoming more like the type of carbon that we burn to produce the energy that we need. Science is a wonderful thing, and one of the things about science is that enable for something to become really truly believable, we have to be able to use it to predict what's going to happen in the future. And we have a lot of that. You may have heard the incorrect statement that 97% of scientists agree that climate change is real and it is human-induced. The reason that is incorrect is that 97% of scientists don't agree. It's very hard to get scientists to agree with each other. But 97% of studies showing anthropogenically induced climate change do show that that is what's happening. And I believe I'm working with a little kind of older data because the study was not done until recently. This is a study that's 4 or 5 years old. In that study, that 2.x amount of papers that didn't support human-induced climate change, well, a further study in 2015 actually went and looked at each one of those papers, and they found that the vast majority of them were critically flawed. So there are lots of biases that are inherent in the publishing of data, and generally negative studies don't get published at the same rate as positive studies, but still, there is just so many of them out there. But more importantly, we can predict what will happen, assuming that our models and our ideas about how climate change works are correct. First of all, we all know this, and we can see very clearly that global temperatures are increasing. So this data here is showing data, instrument data from 1880 to pretty much the end of last year. And this is an anomaly. A lot of the climate change data is presented not as absolute temperature, but how different the temperature is from a particular average. So usually they pick a 30-year period. It's usually either 1970 for 30 years or 1980 for 30 years. And they use that as their baseline. So this is the baseline. And prior to about here, so where's that, 1930s, things were all, the Earth was cooler. And after about 1980, it's never been as warm. We're also seeing warming in the ocean. So this is data that is cycling through. This is showing the actual temperature, so these are not showing anomalies anymore, of various parts of the ocean. So right now it says 0 to 10, here's 10 to 100 meters, here's 100 to 200 meters, and here's 200 to 300 meters. And the red obviously is warm, and the blue is cool. And you can see that there are areas in the ocean that have that are significantly warm. And this is one of the indicators about how the absolute temperature on Earth, if we didn't have the ocean soaking up the heat, the air temperatures would be significantly greater than they are right now. So we're seeing warming in the air, we're seeing warming in the ocean, and that has translated into basically a difference again from average. This is a yearly average, and it just shows how since 1976, which was the last year the Earth was cooler than the 20th century average, we have had warming situations every single year. 2016 was the hottest year on record. It came out on Wednesday, so yesterday NASA reported that 2019 was the second warmest year on record. And that's going to change our climate. This is data from a paper that was published in Nature, which looked at and predicted how the climates would change in a number of cities around the world. And CBC picked this up and made this really nice little infographic showing some of the main Canadian cities. We're not on there, surprise, surprise. But we can kind of guess where we would end up. And so the dot at the current location is what we experience now, and the dot below is what we can expect to experience in the climate. And I can't remember how long it was from now, but it wasn't something that was unimaginable. So, for example, Winnipeg, it'll be more like living down here in southern Minnesota. Now, all this warming means that ice melts. So there's that story as well. The ice melt story is shown here. This is a year's worth of ice extent in the Arctic. So this is showing how much ice is present in each particular month. And so we're starting over there in July, here's September, and up to January. And so basically what this is showing is that in the summer, there's less ice in the Arctic. Northern summer kind of makes sense. Again, this gray line is a median from 1980 to 2010, and then the gray areas come with variation. And these are not all of the years since that average, but these are all of them that fall outside of that range. And so in 2012, we saw the lowest sea ice extent. And in the hottest year, which was 2016, it was also quite low. And here is 2019, and this data ends at the end of October. So that's sea ice. That's ice that's floating on the sea. We also have continental ice. Continental ice is mainly in Greenland as well as Antarctica, and that's what this is showing. This is showing the mass of Greenland ice on the top and Antarctic ice on the bottom over a number of years, back to 2003 probably, ending in 2017, and you can see the downward trend of the ice in both continental regions. So it makes sense. More warming, more ice melt. The age of the ice. So the age of the ice is an indication of how long the ice has been around. And what we see in the Beaufort Sea up here is that generally, look at that. Generally, this is now showing values from the dates up here. So it's been a little bit, oh, here we go. So the dates down here. And you can see this gyre of ice spinning around in the 80s and 90s. And the white ice is old ice, thick old ice that's there for numerous seasons. And the gray, the light gray, is the sea ice that kind of melts and reforms every year. The Beaufort Sea is actually kind of a nursery for this old ice. If the ice is able to stay in the Beaufort Sea for a while before it's kind of spun out over the coast of Greenland and travels down here to have lots of nice icebergs in Newfoundland, this is kind of where it stays for a long enough time that it actually gets nice and thick and old. And we don't see a ton of changes until we get to the 2010s, which is coming up soon. This is just millions of kilometers of ice with different ages. So you can see they're kind of changing. But as we get into 2011, you can see how the ice is becoming much younger because it doesn't have the opportunity to get cooled for long enough to grow that old ice. We've got all this ice that's melting. That water's got to go somewhere. So now we're going to have ice raising the sea levels. And so this data shows ice data, or tidal data, global sea level in centimeters from 1995 to 2018, I believe. And you can see, just looking at the black line, that the levels of water are rising. And they're rising not only because of the addition of that melted ice, but they're also rising because as water gets warmer, it expands. And so the ocean is actually undergoing a thermal expansion, which raises the ice. I can see people are getting so depressed. There's ocean acidification. This is data showing the sea level, or the sea surface pH is becoming more acidic. And that's because it's taking in all that CO2. If you remember back to when I was describing how CO2 dissolves in water, it forms that weak carbonic acid, which is an acidifying mechanism. I think I'm almost done with all of this bad news, which shouldn't surprise anybody. This is something that I find very interesting, and this is something that we're actually going to experience, I think, a lot more. And that is basically the beginning of the instability of the jet stream. So the jet stream is an atmospheric river that circles our globe at about the latitude where we are at. And it is held in place by temperature differentials between the Arctic and the subarctic. So if there's a real difference between temperatures and Arctic temperatures, that is, if the Arctic is much, much colder than the temperate, that jet stream behaves. It stays in place, it wobbles a little bit, but it doesn't get too crazy. However, since the Arctic has been warming at a higher, greater rate than the temperate zones, there has been instability in the jet stream, and it has started to wobble. And when it wobbles, warm air comes up and cold air comes down. So we start to get what is called a polar vortex. So now we experience that here in Saskatchewan a bit. We always have. We've always had cold stretches and warm stretches. But what they don't experience it that often down in the southern United States. And that's when you really hear the people complaining that how can we possibly have global warming? Well, in fact, this polar vortex is an indication of that weakening of the jet stream, which can only happen because the Arctic is warming at a greater rate than the rest of the continent. There's a myriad of other direct consequences, such as the severity of forest fires. I show Canada data here, but of course right now we're more concerned about what's happening in Australia. And of course there's real problems with things like drought. We've just come out of a really significant drought this spring. And of course there's also the opposite of drought, which is deluge or flooding. So there's a lot of direct consequences, there's a lot of indirect consequences, because every time you change the climate of an ecosystem, all of the organisms in that ecosystem have to adapt. And I'm not going to go any further because there's just too much. And I also don't want to depress you anymore. We have a consensus, which is unusual in the scientific community. The consensus is in climate change is happening, and it is human-induced. If you go on to, I didn't put the link on, oh yes, down here, there's a government website that actually lists all of the scientific associations across the world that have signed a declaration admitting that this is the case. Almost 200. And there's some crazy ones out there, but I've just kind of put up the main ones in Canada that have signed this declaration, including the Royal Academy of Science in Canada. One of the courses I teach at the University of Regina is Introductory Environmental Science course. In fact, a couple of my students from this year are here. Thank you. And I tell them at the beginning of the class, I don't know if you remember this, but I remember telling you that I often get really depressed by the end of the semester because I spend the whole semester talking about all of these really depressing stories, like I told you right here today. But there are a lot of other stories that can give us hope and optimism. And a lot of this data comes from experiments that have been done on ecosystems where we apply a stressor, a pollutant or some sort of stress on the ecosystem for a while. We measure what happens when we apply that stressor, and then we take the stressor away. In every single case, increased nutrients, increased metals, what else? Increased acid. These are mostly aquatic systems. If you take the stressor away, the ecosystem has enough resilience to kind of rebound and recover. Now, I'm not saying that that's the case for climate change. I am not a climate change scientist, as I said, so I'm not sure about that. But I think that one of the things that we need to do going forward is, first of all, you have to figure out what you need. And just yesterday, I found this article on the CBC that presented some data from a study that was actually co-sponsored by IKEA and a company called Global Scan. And they went out and they asked 14,000 people in 14 different countries how they defined their relationship with climate change. And they came out with kind of 4 main categories of people's attitudes towards climate change. So in this question of what to do, I'm going to kind of present each one of these categories. The first one, figure out if you are a skeptic. If you are a skeptic, thank you for coming, because this is a really important part of your journey to become a supporter or an optimist. If you're a skeptic, what I would suggest to you is continue to educate yourself and imagine and examine your biases that are inherent in all of us. We all have biases with the way we view the world, and perhaps your biases are kind of holding you back from moving on to a place where you might feel more comfortable making some climate actions. I hope that you're not disempowered. So the second group of people were people that were disempowered. These were people that were feeling that there was no hope, there was no, that it was just so bad that they were paralyzed and they couldn't go forward with any kind of action because of the fact that they just felt so incredibly pressed down by all of these stories. If you are disempowered, one of the pieces of advice that this study came up with was to start joining a collective. So there's lots of examples of how joining a collective can help people feel better and more empowered. And finally, supporters and optimists. If you are a supporter, that's great, and if you're an optimist, that's good too. Because if that, and I would say to you, what do you need to do? You need to go forward with those messages. You need to go forward and tell commercial operations that they need to change, or your politicians they need to change. I don't remember what the bank or the fund, the investment fund was, but 2 days ago it was announced that this particular fund was going to change the way it invested money based on climate change. These are the types of things that will really make big differences. Individually, yes, become part of a motion or movement, a collective. Consume less of everything you can. You know, a lot of people say, well, I don't know what to do with climate change, but I know I can reduce my garbage. It's like, well, that's part of it, right? Every time we make something, we use energy to make it. So if we can consume less of it, we're helping with that climate change issue. Vote with intention. We have a provincial election coming up in the fall, and this will give us an opportunity to have voices heard, and this was very apparent during the federal election in last fall, and continue to learn and spread the word.
First of all, thank you, Britt. I loved the talk. It was really interesting. I've sort of always wondered about, with photosynthesis, what happens to the carbon in the plants that die then, or a tree is cut down, and what happens to the carbon that's stored there. Can you speak to that?
So Sean would like to know what happens to the carbon that is fixed during the process of photosynthesis and once the plant dies. So I could go on and on about this, but basically when an organism dies, it is no longer constrained by life, and it starts immediately to spontaneously dissolve due to kind of thermodynamics. And the energy that's stored in those carbon-carbon and carbon-other bonds is spontaneously released as decomposition happens. Decomposition is fueled, or no, not fueled. Decomposition is done by a lot of different organisms. And so what they're doing is they're taking that energy and that carbon into their biomass as energy. And so when they do that, they will excrete products, including CO2 if they're aerobic respirators. If they're anaerobic. The bacteria will process it. I'm not exactly sure how I can answer this in a short way, but suffice it to say that when organic material that has been made from carbon, that has been fixed from the atmosphere, decomposes, eventually that CO2 will end up back in the atmosphere. So it closes the loop.
Thank you. Any other questions?
Yep. Thank you for the talk. Very interesting. So where do we get our best bang for our reversing this buck?
Where do we get our best bang for reducing this issue, right? Reducing our footprint, is what you're basically saying. I'm not sure I can answer that. What I can say is that one of the people that I forgot to mention in our AFC series is Britt Hall, who's an economic professor, and he will be speaking about the carbon economy. Most economics will agree that pricing the pollution is one of the most effective ways to get to reduce our emissions. So he will talk about that, and the other thing that can really help is electrifying a lot of things. So it doesn't work that well in Saskatchewan because our electricity is mainly made from coal, which is a hydrocarbon, and it reduces a lot of carbon dioxide and other greenhouse gases. But if we can clean up our electricity sources, we can use kind of renewable solar, wind, hydro, that kind of thing, and then increase that infrastructure, electrify everything with clean energy, electricity, and that will make a large, that will help a lot to get us to the point where we will get to what they call net zero. She was asking about the values that I showed, looking at the difference in the concentrations of all of the greenhouse gases, pre-industry versus modern. There's some really fantastic resources out there. Many of the, majority of the data that I took today were from places like NASA and NOAA. These are large earth science organizations that collate a lot of different data from a lot of different sources, put it together so that we can trust and it can be robust. And in fact, if you go to this site right here, that actually gives us real-time, almost real-time values of how much carbon dioxide is in the atmosphere. So you can actually go and see what the concentration was on January 5th or whatever date you want. So I can't remember exactly where I got these data, but there are a lot of very reputable earth science databases that collect this type of data. And the data from pre-industry, that would have been data that were taken from these ice cores, where you can actually look at the bubbles that are trapped in the ice and measure the concentrations of the gases in the actual bubbles. And then you can use the material in the ice, like the dust, to give it an age to that spot. And then that will actually give you the concentrations there.
I've seen a lot of interesting data here this evening,
Yes.
but we haven't really talked very much about,
What?
okay, so now what?
Yeah, no, and that's a good point. And again, I'll kind of point to the talks coming up. I will say, I hear you exactly. Many people disagree with this, but I tell my students in my class that there is no way I'm getting on a jet plane that runs on solar. Like, no, I'm not flying on a plane that is an electrical plane, even though they've started to do that. There were a couple of flights that happened to DC in the fall. So you're right, there's going to be this period of transition between when we, from now to when we need to get to the point where we're saving that really good stuff for the jets, or maybe even we're using nuclear for jets or whatever. And this is the question, what do we do? What do we do? And I think that one of the things that I've found helpful is by doing whatever I can in a group setting that will allow me to have the support of people that are in like minds and have the kind of similar goals. So I wish I could answer that. I think one of the most important things we can do is we can keep voting so that we get progressively more friendly governments in that will make some of these big changes that people generally don't like, but that have to be done.
So the academics for climate change, are you advocating for some change within the university? Are you trying to go down that path?
Yes, actually, we have just in the last semester, a group of us started to get together. Some of us are here, some of us are actually out there because we couldn't get in. But one of the things that we did is we presented a motion to our upper administration in what we call faculty and council. So all of the academics get together, and this is where we can make suggestions to our leadership team. And it was pretty much unanimous that we passed two motions. One of the motions was that the university accept that we're in a climate crisis, and we work towards reducing our carbon use. And the other one was that we actually start measuring what we use and reporting that so that people out in the public, we're a public institution, we are actually beholden to the public, so that the public can actually see, oh, look at, they've reduced their energy by replacing all of their high energy lights, for example, or they reduced their amount of water that they're using. So both of those motions were actually accepted unanimously. So that's very, very good. We also have a new strategic plan that is currently being assembled, and the strategic plan is actually led by Carrie Finley, which is giving the water talk. And there has been a lot of dialogue between the strategic plan and academics about how important climate action is to the university's next 5 years. And so that will be coming out. I'm not saying that it's going to be in there, but
Here it's up to date. In 2 months we'll see.
yeah, exactly. But so there is a voice there, and it's being heard, I think.
Great, thanks for that.
Yeah.
Suppose that we turn it all off, stop burning everything, which is not really practical, but suppose we did. How long till it goes back to normal?
I don't know that question. That is just a question. Does anyone in the audience, any of my colleagues here, know the answer to that question? I mean, it depends on a lot of things. It depends on exactly how much more carbon dioxide the ocean can actually take up. There is some thought that we're getting to kind of peak carbon dioxide in the ocean. And if that's the case, then the recovery will be longer. I mean, eventually, Earth is a closed system. There's only so much carbon and oxygen in here, and if we give the Earth enough time, it will go back to steady state in which sources are equal to cities. How long that is, I suspect, is a very, very long time.
One thing that we can look to is maybe the reformation of the ozone layer. So we did sort of start eliminating the fluorocarbons and that type of things as a global community, decided to do that, and then the ozone layer has recuperated, right?
It's one of the feel-good stories in environmental science, and it was born in Canada. The international treaty that kick-started the reduction of those chlorofluorocarbons was signed in Montreal, and it is one of the most successful environmental treaties, global environmental treaties that are out there. There's a number of differences between that problem and climate change. First of all, there were substances that could replace the chlorofluorocarbons and still give that function. It turns out maybe some of those are contributing to ozone depletion as well, but at the time there was, and it was also kind of, we know the chlorofluorocarbons are mostly used in refrigerants and propellants, and so it was relatively easy to, stop using those products, especially because there were alternates. So there is a little bit of a difference, but it is something to remind yourself of, and a reason that an optimist would be able to continue to work towards climate action.
What would you say is, the best clean energy resource production for Saskatchewan or Canada to generally explore in terms of resources invested into these infrastructure and everything versus the waste produced?
This is a great question to ask Brett, our economic professor that's coming at the end of the series. You're right, every single thing is going to have a footprint. We build solar powers, we're going to use all of those trace metals to build those power grids. We use wind power, there's risks to wildlife. Hydropower floods land, causes mercury and greenhouse gas emissions on its own. So there's not a lot of great options that have no footprint. So it comes to the point where you have to start thinking about what's kind of the best option. And unfortunately, I cannot speak to that. I don't know. It is a good question.
Okay, let's thank our speaker once again.